Now in this lesson, we're going to be focusing on the operations with radicals. So by operations, when you hear that in math, you should be thinking addition, subtraction, multiplication, and division. So by addition, subtraction, and multiplication, it's going to be exactly what you'd expect. We're going to be dealing with taking a radical plus a radical, radical minus a radical, radical times a radical. Now with division, we will be having dividing by radicals, but really our overall goal there is just going to be get the radical out of the bottom. And we'll explain why when we get to that point. But that's what's going to be going on for this lesson. We're going to focus on those four operations: addition, subtraction, multiplication, and division. Now we previously saw that radicals are really just exponents. So as we start to think about operations with these radicals, we're basically going to follow the same rules as operations with exponents. So when you were trying to add and subtract, when you had x to certain powers, all you did is you combined like terms. And what it meant to be a like term was that your bases were the same, so you had the same variable, and you had the same power. And so it's going to be the exact same thing when we're dealing with radicals, is we're going to say, I need to have what it is that I'm taking to the power, which is the stuff underneath the radical, and the power itself needs to be the same, which is going to be your index. So if you have the same index and the same radicand, then you have like radicals. At which point you're going to follow basically the same rules as combining like terms. And if you think about what it meant in combining like terms, is you just took your coefficient of x and your other coefficient and you add them together. And you kept the same term, the same x to a power. And so that's all we're going to do with radicals too, is add the coefficients that are in front of the radicals if the radicals are exactly the same. So let's take a look at our first example. In option A here, we have 4 square root 11 plus 8 square root 11. So we want to first of all identify if these are like radicals. Do we have the same index? Well, yeah, they're both square roots. Do we have the same stuff underneath the radical? Yeah, they're both square root of 11. So all we're going to do is add the coefficients. 4 plus 8 is 12 square root of 11. So I had 4 square roots of 11 plus 8 more square roots of 11. So I've got a total of 12 square roots of 11. If I'm just kind of counting stuff, if you have 4 blahs plus 8 more blahs, you have 12 blahs. That's what's going on here. So same thing for B here. They're both cubed roots, so we got the same index. They both have a 3x underneath, so we do have like radicals. So all we want to do is look at 5 minus 7 is negative 2. And then we keep the same radical, cubed root 3x. Pretty straightforward, pretty simple. Now at its core, adding and subtracting radicals really is simple. But of course there's going to be curveballs. There are times where our radicands don't appear to be the same, so it looks like we don't have like radicals. But in actuality, we do. And what's going on here is we need to simplify our radicals. So we need to simplify them to see what is the radical that's really at the core there once we get all the fluff out. So if I was trying to add square root 20 and square root 45 together, on first glance, they are not like radicals. But if I go through the break it up, take the radical, clean it up process, things might change. So square root 20 is square root 4 times square root 5. Square root 45 is square root 9 square root 5. When I take the radical, this becomes 2 root 5 plus 3 root 5. Now all of a sudden they are like radicals. They're both square root of 5. So now we can just add their coefficients to get 5 root 5. And so this is why in the last lesson I said that simplifying radicals was so darn important. It was the most important thing we'll do in this entire unit. We need to do simplifying radicals twice just to do this one problem. Now once we successfully simplify both those radicals, the rest of the problem, the actual new part, the adding part, was simple. And so really your work right here in these types of problems is just going to completely hinge on your ability to simplify radicals. All right, so let's do a couple more examples to make sure that we're comfortable with adding and subtracting these radicals. So our next example here, we have the square root of 12 plus 3 square roots of 27. So I'm going to break up the square root of 12 as the square root of 4 and the square root of 3. Now the cool thing about these problems with adding and subtracting radicals is that we get ourselves some hints on the simplifying aspect of things. So of course my 3 is going to copy down, but as I'm looking at 27, if I'm going to have like radicals, then they're both going to have a root 3 in them. So that kind of gives me a hint that it must be 3 times 9. This isn't always going to work, but it's a great place to start. Now once we do this, now we can do the take the radical step, which gets us 2 square root 3 plus 3 times root 3. Now we do the clean it up step. 3 times 3 is 9. That's part of my clean it up step. Now that I'm done with the 3 steps of simplify, now this is just that easy idea of combining like terms. Those are both root 3's. 9 plus 2 is 11. So this is just 11 root 3. So let's look at the next example. Cube roots and the numbers are getting a little bigger. But again, if we use that same idea of a trick, it's not a guarantee. But if these guys are like terms, they're going to have cube root 2's in them. So as I try to do the break it up step with 54, if I had to guess, I'd say I'm probably going to be left with a 2. And sure enough, if I did that, I'd be left with 27, which is a perfect cube. So if I did the same thing with the 16, said, hey, maybe he's a 2 as well, it'd be 2 times 8. And 8 is a perfect cube. Now the other thing that I would do on these problems is I've got that plus cube root 2 at the end. I'd actually write his coefficient of 1 if I were you. It might help. So we've got the cubed root of 27 is 3 in our take the radical step. Cubed root of 8 is 2. Now in the clean it up step, it's a small clean it up step, but we'll go ahead and do it anyhow. 5 times 2 is 10. So now all 3 of these are cube root 2's. So now I just want to look at my coefficients. 3 minus 10 is negative 7. Negative 7 plus the 1 is negative 6. Cube root 2. Let's go ahead and do one that's got some variables in it. We're still going to do the same thing as far as break it up, take the radical, clean it up. We're going to break up 48 as 8 and 6. We're going to break up y to the 4th as y cubed and y to the 1st. And then we're going to look at the second guy. Cubed root 6 doesn't simplify, but the cubed root of y to the 4th, I could break that up as y cubed and y. There's my break it up step. Now let's take the radical. Cubed root of 8 is 2. Cubed root of y cubed is y. Everybody else just copies down. We've got cubed root of 6 and cubed root of y. We've got the cubed root of 6, cubed root of y. And now let's clean it up. Now in the clean it up step, we're going to clean up everything to the left of the plus, and then we'll clean up everything to the right of the plus. So keep in mind each of those are their own individual terms, and so they get cleaned up independently of one another. So for the highlighted yellow one, the stuff outside the radical is 2 times y. Inside the radical, I have a cubed root of 6 and a cubed root y, so we can write that as cubed root 6y. Now for the stuff underlined in teal, outside the radical, I have a y. I'm going to write one y because again, it helps sometimes when we're talking about coefficients to explicitly write that one. Now we want to say, do we have like radicals? I have y cubed root 6y. I have y cubed root 6y. Those are the same. So I'm going to add my coefficients of 2 and 1 together to get 3. Y cubed root 6y. And that's my final answer. So now let's talk about multiplication with the radicals. The main thing I want you to look at when multiplying radicals is just to follow all your normal rules of multiplication, whether it's distribution, FOIL, whatever's going on, we're going to follow all our normal rules. But when we're dealing with the radicals, what I want you to notice is that we will have things that are outside the radical, like in this case, the 5 and the 3, and we'll have stuff that are inside radicals, the square root of 2x and the square root of 3y in this case. So we're going to handle this just like the clean it up step that we've already been doing a bunch. Is when we're multiplying, we're going to say, let's take everything that's outside the radical and let's multiply it together first. So in this case, 5 times 3 is 15. And then we're going to take everything that does have a radical and multiply it together. So square root of 2x and square root 3y becomes square root 6x times y. And that's really all I want you to focus on when talking about multiplying with radicals, is that we're going to multiply the stuff that's outside the radical together and multiply the stuff that's inside the radical together. And that's about it. So we're going to walk through some examples of how multiplication can come up, but they're really just things that you've seen before. In this first one, we have a single number followed by a parenthesis with addition. This looks an awful lot like distribution to me. And that's all we're going to do. We're going to distribute the square root of 3 to the 5, and then distribute the square root of 3 to the square root of 30. Now, root 30 times root 3 will be root 90. And then once we finally get some sort of answer, we're going to try to simplify any radicals that we have. Now, root 3 doesn't simplify any further, but 90 would be root 9 times root 10, which would be 3 root 10. And so that's it. We're going to distribute. If we have a radical times a radical, we can multiply them together, but then we're going to simplify in the end by doing the break it up, take the radical, clean it up. Now in each of these examples, it should jump out at you as a FOIL problem. So let's go ahead and do it that way. Let's look at FOIL. Our F is a radical times a radical. That's root 35. Our outside is 1 times a radical. So that's root 5. Our inside. Now we can look at this as things outside the radical, because outside the radical I have a negative 1. So outside the radical is a negative. But then inside the radical I have root 6 times root 7 is root 42. And then the L part of FOIL, negative times 1 is negative, and then root 6. None of those numbers can be simplified, and so those 4 terms are really our answer to the first part of this example here. So let's move on to the second part of the example. The second problem here. Now we can again look at this as a FOIL problem. For our F in this case, let's multiply the things outside the radical. 7 times 3 is 21. Then we'll multiply the radicals together. Root x times root x would get me root x squared. That's the F part of FOIL. Now let's do the O part of FOIL. Outside the radical, I have a 7 and a -1. Don't forget that negative there. That's going to get me -7. Inside the radical, I have a root x and a root 5. That's going to get me root 5x. Now we'll move on to the I part of FOIL. Outside the radical, I have a 5 times a 3. That's 15. Inside the radical, I have an x. Now let's try the L part of FOIL. Outside the radical, I have a 5 and a -1. That gets me -5. Inside the radical, I have a root 5. Now there is one little bit of simplification we can do here because the square root of x squared is x. Other than that, none of the rest of this simplifies, and we're just going to have all the rest of these terms. And that would be our final answer. Now we could go ahead and FOIL this problem out as well, but it's going to be much easier if we realize that this problem looks an awful lot like an a minus b times an a plus b situation, where my a is the square root of 2x and my b is a 5. And I know that if I multiply a minus b times a plus b together, that the answer I get should be a squared minus b squared. If I square the square root of 2x, I'm going to get 2x by the definition of a square root. Squares are going to undo square roots. So I know I just get 2x there. And if I square the 5, I get 25. So this is an example where knowing your formulas from earlier on in the semester are really going to help out and make your life a lot easier, especially once we realize that when you square a square root, those two things just kind of undo each other. The square and the square root undo each other, leaving us the 2x. That makes life kind of easy. So let's take a look at this example where we're squaring two terms. Now again, we could FOIL this out. We could rewrite this as the square root of x minus 3 plus 5 times the square root of x minus 3 plus 5, and then FOIL it out. And I will tell you that when I see students do that, I see a lot of errors popping up. If you could remember all the way back to lesson 1, we went over a formula that I said, if you can use the formula instead of FOILing it out, you're going to really enjoy it when you get to Unit 4. Hey, we're in Unit 4. So, let's take a look at this. What you should see when you look at this particular problem is you should see that we're looking at an a plus b squared, where the a is the square root of x minus 3 and the b is 5. And when you have a plus b squared, that ends up being a squared plus 2ab plus b squared. And way back in lesson 1, we said for that 2ab, think about that as just 2 times the product of whatever you had. So in this example here, where a is the square root of x minus 3, if I were to square that, the square and the square root undo each other, and they just leave me x minus 3. Now for the 2ab part, let's come off to the side to talk about the 2ab part. It's 2 times the square root of x minus 3 times 5. Well, the 2 is outside the radical. So really what you want to do in the 2ab part is take 2 times whatever is outside the radical. In this case, it's 5. 2 times 5 is 10. And then times the radical. And that's all the 2ab part is. 2 times whatever is outside the radical times the radical. And then 5 squared is 25. Now we do have a little bit of combining like terms that we can do because I do have a -3 and a 25. So I have my x. I've got my 10 square root x minus 3. And then when I combine like terms, I get plus 22. And there it is. So we're about to move on to the whole division part of our 4 operations that we're looking at with radicals. And I just want to do a little bit of motivation. So what we're doing here is not the type of problems that we're solving. This is just to kind of explain the motivation behind what it is that we're actually doing. So suppose I asked you to do each of these 3 division problems, and I told you to get me an answer rounded to 2 decimal places. So let's go ahead and go through this, and basically what we're going to do is long division. And don't get me wrong, we're not doing long division in this section. This again is just part of the motivation behind what we're doing, so you can kind of understand the purpose and what it is of why we're doing. So looking at this first one, we're dividing 2.1 into 1.7. Now, if you remember from your whole rules of decimals, what we want to do is we want to move the decimal point 1 spot to the right in each of these. That's kind of like in the original problem multiplying by 10 over 10, which is 1, which is legal. And that's kind of what's going on here. So we're really doing 21 into 17. So our decimal point's actually right there. Now 21 won't go into 17 at all, so we actually need to put another 0. 21 is going to go into 17. Let's go ahead and try maybe 8 times. So if I do that, that'll get me 168. I subtract that to get a 2. I carry down another 0. 21 goes into 20 0 times. So I bring another 0 down. And it's going to go in there a few times actually. So it's going to go in 9 times, and that's going to get me 189, and I can really stop there since I only need to round to 2 decimal places. Since I needed to round to 2 decimal places, my third decimal place is large enough that I need to round up. So even without a calculator, I can see that this rounds out to 0.81. Fair enough. Let's keep going. Pi divided by 2.1. So hold on a second, pi. So pi is this irrational number that goes on and on forever. So we're dividing 2.1 into pi. And so again, pi is 3.14159265335. It keeps going for a long time. So if I move the decimal place 1 spot over, cool, now I can actually do this problem. 21 goes into 31 once. 21, 10, drop the 4 on down. We're going to go into there. Oh, it doesn't quite go 5 times, so I got to go with 4 times instead. That's going to get me 84, subtract is 20. Now we're going to bring this 1 down. We're at 201. So we're going to say, how many times does that go in? I don't know, maybe 9 times. So that's going to be looking like 189. So we got 12. Let's drop the 5 down. If I can figure this one out, it's enough to round to 2 decimal places. So 21 goes into 125. Not quite 6 times, but it does go at least 5 times, which is all that really matters. This allows us to round this to 1.50. Okay, so we got an answer, all well and good. So we were fine when we had a terminating decimal divided by a terminating decimal. We were even okay if we had an irrational number, a decimal that goes on and on forever with no repetition. We were okay if we had an irrational number in the top. Now let's look at what happens when we have an irrational number in the bottom. When I have 3.1415926535 blah 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 forever, into 2.1. Well, our first step in order to do this problem is to move the decimal place over, hold on a second, over, oh my goodness, it doesn't end. How many decimal places do I need to move this over? An infinite number. I can't do this. I don't know how to accurately do this problem. I don't know how many decimal places to move this over because there's an infinite number of them there. So the moral of the story is an irrational number in the bottom is a bad thing. I can't get a good approximation of this if I have an irrational number in the bottom. So that's the motivation behind what we're going to do, because what we're actually going to do is not called dividing radicals. What we're going to do is actually called rationalizing the denominator. We're going to start off with a problem that has an irrational number in the bottom, a radical in the bottom, and we're going to do some work, all legal work, until we no longer have an irrational number in the bottom. The irrational number will be in the top instead, but that at least makes it so that we could do division if we wanted. And like I said, we're not actually going to do long division. This was just motivation to show you why an irrational number in the bottom is a bad thing. So let's look at this whole idea of rationalizing a denominator. If I'm dealing with 2 over the square root of 5, I want to get rid of the square root that's in the bottom there. It sure would be nice if I could just square it. No, I can't, so don't write that. I can't just square it, so that kind of sucks, but it would sure be nice if I could. That'd get rid of the square root. Well, what does it mean to square something? Well, it means to multiply it by itself. So it'd be sure nice if I could just multiply by the square root of 5. Well, I can't do that, but what I could do is I could do it on both the top and the bottom. In doing that, I'm multiplying by 1. That gets me 2 root 5 in the top and the square root of 5 squared in the bottom. And the square root and the square undo each other, leaving me just the 5. And so now I no longer have a square root in the bottom, which was my whole goal, really. Now, I do want to point out, we don't just multiply by whatever's in the bottom. On this next example, we're not going to just multiply by the square root of 9x. Our goal is actually to bring ourselves up to a perfect square. So one thing I want you to do and to get in the habit of, and we've mentioned this before, is anytime you have a number that can be written as a power, do so. So 9, you want to write it as 3 squared. And the reason for doing that is we see this is already a square. I don't need to mess with that portion of it. The only thing I need to mess with is the x. I need to bring the x up to a perfect square. So I have one x there. I'd like 2 of them, so I need 1 more. So I multiply by root x over root x, getting me 5 root x in the top. And in the bottom, I've got the square root of 3 squared and the square root of x squared. The square roots and the squares undo each other, so that in the bottom, all I have left is 3x. Now, in the last example, I sort of just kind of walked us through in a willy-nilly way how to rationalize the denominator, but let's try to get a process out of this. And I sort of mentioned some of the items in the process, but I think it's really important for us to write this out and to have it on paper for what we really want to do every time. So one of the things that we saw is anytime you can write a number, do so. So if you see 8, you're going to rewrite the number 8 as 2 cubed. So anytime you have a number that can be written as a power, do so. And then when it comes to rationalizing denominators, your whole goal is to be able to take the radical. So kind of like the whole simplifying idea is to say, when can I take the radical? Well, if it's a square root, if you have a perfect square. If you have a cubed root, then you need a perfect cube. If you have a fourth root, you need a perfect power of 4. So the right questions you want to ask yourself is how many of whatever it is do I have? So if I have x's, if you have x squared, you have two x's. How many do you want to have? Well, if you're trying to take a cubed root, you want three of them. If you're trying to take a fifth root, you want five of them. So your next question is, how many more do I need? And once you figure that out, that's what you're going to multiply the top and bottom by. You're going to bring yourself up to however many you need of whatever it is you're looking for. Now, I know without an example, these steps kind of look a little bit weird. So let's go ahead and look at an example, and we'll keep on coming back to those three questions. How many do I have? How many do I want to have? And so how many more do I need? So here's example 8, and directions are to rationalize the denominator. Now, for the first problem, our denominator is cubed root of 2. So let's go through our three questions. How many do I have? And so we're talking about 2's. How many 2's do I have? I've only got one of them. How many do I want to have? I want to have 3 of them. I want to have a perfect cube. So how many more do I need? I need 2 more. I have 1, I want 3. And that's what we multiply by in the top and the bottom. We multiply by 2 squared. Well, what is 2 squared? 2 squared is 4. Now, I'm not going to write that in the bottom, though. In the bottom, I'm literally going to write 2 cubed, because I had 1 2 originally. I multiplied by 2 more. That gets me 3 of them. And I write it in that way in the bottom because it makes it more clear that my cube root and my cube undo each other. And when they undo each other, all I'm left with is the 2. And I have successfully rationalized my denominator because I no longer have a radical in the bottom. Let's go ahead and look at the second example. In this second example here, we have a 9 in the bottom. Whenever you have a number that can be written as a power, do so. So our first thing we're going to do is rewrite this as 3 squared. Now, how many do I have? How many 3's do I have? I have 2 of them. How many do I want to have? I want to have 3 of them because I have a cube root. So how many more do I need? I only need 1 more. That's what I multiply by in the top and the bottom. So in the top, I have 2 cubed roots of 3. And in the bottom, I've got the cubed root of 3 cubed. But again, the cube root and the cube undo one another. So that all I'm left with is a 3 in the bottom. And now I've rationalized the denominator. Let's go ahead and go to the third example. So now again, I have a 9 again. So I'm again going to rewrite this original problem before I start asking my questions. Where the 9 I'm going to write as 3 squared. And then I still have the x to the 4th. Now I know I'm going to need to multiply by a cubed root in the top and a cubed root in the bottom. So I'm going to go ahead and start off with just that written out. Now as I go through my 3 questions, I need to rationalize for both the 3's and the x's. And I'm just going to treat them separate. I'm going to start off with just looking at the 3's. Just looking at the 3's, how many do I have? I have 2 of them. How many do I want to have? I want to have 3 of them. So how many more do I need? I need 1 more. Then I move on to the x's. How many x's do I have? I have 4 of them. How many do I want to have? Well, I want to have a multiple of 3. So I would like to have either 3, 6, 9, 12, etc. 3 is too small because I already have 4 of them. But then how about 6? I could build myself up to 6. So if I want to build myself up to 6, I need 2 more. So that's what I'm going to multiply by, is the 2 more that I need. So up top, I have cubed root of 3x squared y squared. And in the bottom, I originally had 2 3's, now I've got 3 3's. I originally had 4 x's, now I have 6 x's. My top doesn't simplify at all. My bottom, cubed root of 3 cubed is 3. Cube root of x to the 6th is x squared. Because remember, that's 6 over 3, that's x squared. And there's my answer. Now, what if I wanted to rationalize the denominator of 1 over 1 plus the square root of 2? So if I were to multiply the top and the bottom by 1 plus the square root of 2, then what's going to happen on the bottom? Well, on the bottom, I'm going to end up with my middle term. That's no good. I still have a radical. So I can't just multiply by 1 plus root 2 because of the middle term. So I got to think back and say, what formulas do I have that make it so there is no middle term? And what should jump out in our memory is a plus b, a minus b. When you multiply those together, you get a squared minus b squared. Everything's squared, which means if there's any square roots in the original problem, then they would be gone. That's kind of cool. So maybe if I multiplied by 1 minus the square root of 2 in the top and bottom, that would create an a plus b, a minus b situation. That'd work out pretty nice. So let's look at some examples that involve multiplying by the conjugate. And that's the fancy word for when you change the sign in between the two terms, is the conjugate. So in this first example, I'm going to multiply by the conjugate, which is square root of 3 minus 1. And I'm going to do that in the top and the bottom. Now I'm going to suggest in the top that you leave this factored for now. Leave it as 2 times the square root of 3 minus 1. Don't distribute the 2 quite yet. Now on the bottom we have a squared minus b squared. When you square the square root of 3, you get 3. And then you get your minus 1. And then you should probably quickly see why I want you to leave it factored in the top, because if we're going to be able to simplify anything in the bottom, being factored is nice. So that's just the square root of 3 minus 1. Now let's look to the second example on here, which is a little bit trickier, but the basic process is not tricky. The basic process is pretty easy and obvious, that all we're going to do is multiply by the conjugate. Now the process that we go through requires a couple more steps in this particular one though. Now up top, we're going to keep it like the last one. We're going to leave the 5 on the outside for now. Maybe that'll change later, we'll see. But now in the bottom, we got to be careful, because when I do my a squared, when I do 3 root 5 squared, I'm going to square the 3 and square the square root of 5 to get 5. So my a squared is 45. My b squared, 2 squared, is just 4. Now I can do my subtraction of 45 minus 4, which is 41. And at this point, I can see that having that 5 out in front isn't helping me. So I would go ahead and distribute it and get 15 root 5 minus 10. Let's go ahead and look at the third piece of this. The conjugate of root 3 minus 5 is root 3 plus root 5. All we're doing here is changing the sign between them. Now in this problem up top, we're going to need a FOIL. First, outside, inside, last. And on the bottom, a squared minus b squared. Up top, we have root 6, root 10, 5 root 3, 5 root 5, and on the bottom, negative 2. Now, I do want to remind you, we do not ever leave a negative in the bottom. So what I would do if I were you is I would erase the negative in the bottom and just put it in front of the whole thing. And that's better mathematically. Our next set of directions are going to be to rationalize the numerator. Now, I want to take a moment to point out that this kind of goes against our whole motivation behind why we want to do this in the first place. I'm not going to give you a ton of work when it comes to rationalizing numerators, but I do want to talk about it briefly, just because it does come up sometimes when you're dealing with trigonometry, for instance. There's times that we want to say, let's get the radical out of the top and into the bottom to see if we can recognize it to be similar to one that we've seen before. So, with that said, let's go ahead and look at two examples. One in which we have a single radical in the top that we want to get rid of, and one in which we have a single radical in the bottom that we want to get rid of. Or sorry, one in which we have two terms in the top that we want to get rid of. And we're basically going to handle this just like rationalizing denominators. The only difference is we're going to look at the top. Now, for the first example, the first thing I would actually do there is I would simplify this whole fraction. Because with 32 over 80, there's a 16 that goes into both of those. So really that root 16 or 4 goes away, and it's just root 2 over 5. So that's always something to look for when we're trying to rationalize either numerators or denominators. Now, since our goal in this problem is to rationalize the numerator, we want to multiply by whatever it takes in the top to bring it up to a perfect square. So that's going to be root 2 over root 2. That's going to get us 2 in the top, root 10 in the bottom. And that's actually the answer for rationalizing the numerator. Now, for our other example that had two terms in the numerator, like we did with denominators, in order to rationalize this, we're going to multiply by the conjugate. So we're going to multiply by root x plus 3 in the top and the bottom. So that up top, that's a difference of squares. We're going to have root x squared is x, minus 3 squared is 9 in the top. And in the bottom, we're just going to distribute that 4 across. And so I know I kind of rushed through this a little bit, but honestly, we're not going to do a whole lot with rationalizing numerators, and it should be fairly straightforward and simple, that you basically do the same thing as what you would have done with denominators, you just do it to the numerator instead. So there you go.